Hey everyone, today I'll be going over the problems from the 2023 F equals MA exam. So starting with problem number one. So you have a bead on a circular hoop with radius 2 meters that travels counterclockwise for 10 seconds and completes 2.25 rotations, at which point it reaches the position shown. And so you want to find the average speed and the direction of its average velocity in the past 10 seconds. So you know that average speed is just uh, distance over time. So average speed is distance over time. And so you know that it completes 2.24 rotations. So 2.25 rotations would just be 9 over 4 rotations times the circumference of the circle, which is 2 pi r. And so r is given to be 2. There's 9 over 4 times 4 pi, which would be 9 pi. And you know that time is 10 seconds, so the average speed is going to be 9 pi over 10. So 9 pi over 10 meters per second. So it's either C or E. And so the direction of its average velocity, well, you know that the distinction between average speed and average velocity is that average velocity is displacement over time. So if we look at displacement, we know that after two full rotations, so you know it starts from here. So after two full rotations, displacement's going to be 0 because it ends up at the same position. So what our displacement's going to be is just the initial position and the final position. So from the initial position to the final position, the direction of the average velocity is going to be something like this, which means it should be E. So our answer is E. Okay, moving on to problem number two. So you have a mass on an ideal pendulum that's released from rest at point 1. When it reaches point 2, which of the following shows the direction of its acceleration? Okay, so we know that it starts from here, and we want to find the direction of its acceleration when it's here. So what we can do is that we can break up its acceleration into two components. So one is going to be, so if the path is like this, so one's going to be tangential to the path, and one's going to be pointing towards here, which is centripetal acceleration. So we know that centripetal acceleration is v squared over r. And so since it's moving downward, basically starts from rest, and so it moves down, let's just say a height h, that means it has to have some kinetic energy here. So centripetal acceleration is going to be non-zero. It's going to be pointing here. And we also have tangential acceleration. And so since it has some velocity, and it's basically accelerating in this direction, which means that its velocity increases as you go down, must also have some tangential acceleration. So since it has acceleration in this direction and in this direction, its net acceleration must be here. Which means it has to be B, because A is basically centripetal, C's are tangential, so B has to be between. Okay, problem number 3. So we have a soccer ball that's kicked up a hill with a flat top as shown. The ball bounces twice on the hill at the points shown and then lands on the top and begins rolling horizontally. So we know the vertical component of its velocity as a function of time. So we know that, so as you kick it, you're gonna have gravity acting downward, which is going to reduce your vertical velocity. And as you can see, it becomes flat here, which means your vertical velocity is 0. And then it goes down a bit more. It's still accelerating. So it's going to have some negative velocity here, negative vertical velocity. And then it's going to collide with the plane, which basically means that its vertical velocity is going to change direction. So what we want our graph to look like, I mean, something like this. So know that we have vertical velocity, we have time. So it's going to start some positive quantity It's going to be linear because we always have the same gravitational acceleration. It's also going to pass 0. Then suddenly, when it's at some velocity that's smaller than this, it's going to collide. And so it's going to change direction. It's going to go like this. And it's going to move down again. It's going to collide, move down, collide. So it should look something like this, which best represents E. So E is our answer. Okay, so number 4, we have a box of mass m that's at the bottom of an inclined plane. Angle theta to the horizontal and height h. So you have a person dragging the box up the plane, applying a force parallel to the plane. Coefficient of kinetic friction is mu k, and you want to find how much work the person has done. So you know that work is just the dot product of force and displacement, which basically means that if we have a displacement here, we want to find the magnitude of the force in the displacement in the direction of the displacement. So we'll say the x component of it, and so the work done across here would be Fx times our displacement. So similarly, in this situation, our displacement is happening here, and we're already given that the force is parallel to the plane. So this is the direction of our force. And so basically what we want to find is our force times our displacement. So we know that it's the box is dragged very slowly up. And so what that implies is that throughout we can assume that the net force on this block is 0, but it's like still moving up. So it's very close to 0, but it's still like, a very small positive quantity. So the other forces acting on this block are mg sine theta, which is downward, and friction, which is going to be mu k mg cosine theta. So we know that F equals mg sine theta plus mu k mg cosine theta. And so the work done is going to be, well, this is h. And so sine theta equals h over x, which means x is just h over sine theta. So if you want the work, it's going to be Fx, which is mgh plus mu k mg cotan theta, which would be E if we factor out mgh. So yeah, mgh cotan theta. Okay. Problem number 5. 2 blocks of mass m and a block of mass 3m are attached to a system of massless fixed pulleys, and massless string is shown. I want to find the acceleration of each mass m. So it's actually a pretty simple problem because we just have to write out the equations, acceleration, each of these blocks. Okay. So we have these pulleys here attached to 3m. Okay, so we assume that it's accelerating downward, which it will because this mass is greater than these two combined masses. Then if we assume that there's a tension here, T, uniform tension throughout this string, which is true because it's massless. That means the tension here also has to be T because it's symmetrical. So 3mg minus 2T equals 3ma. And if we consider any one of these, since it's moving up, T minus mg equals ma. So if we solve for a, we can basically multiply by 2. We can add these two equations. And we get that A equals G over 5, which gives us B. Okay, moving on to problem number 6. So you have a ball at the end of a rope of length 0.5 meters that's swung in a horizontal circle with a speed of 15 meters per second. And you want to know the height difference between the ends of the rope. So I have this ball, this length L, let's say this is theta. You'll find this height H. And you know that this ball is moving in a horizontal circle with speed V. And you're given the speed, you're given L, and that's it. Okay. So you know that there are two forces acting on the ball. So there's gravity and there's tension. And you know that there's so gravity can't provide any centripetal force to the ball. It's completely vertical. So tension has to do that. So if we consider that this is theta, that means so it's gonna be theta. So T cosine theta is gonna be providing your entire centripetal force. And T sine theta is gonna be equal to mg because it doesn't accelerate vertically, so it's stationary. So now if we plug this in for T, we get that mg cosine theta over sine theta equals mv squared over r, where r is just L cosine theta. Okay, so if we look at the answer choices, we can see that the height difference is extremely small because they're 100 centimeters and 1 meter. So if the height difference is really small, then that means that theta is really small. So what we can do is we can use a small angle approximation for theta. So we can see that we can basically approximate cosine theta to be approximately 1. So now we have that mg over sine theta equals mv squared over L, which means that sine theta equals GL over V squared. So which is 5 over 15 squared. So arc sine of 5 over 225 is 1.27 degrees. And so since we want to find L sine theta, so H equals L sine theta. So it's going to be 0.5 sine theta. Alright, actually we didn't even have to calculate theta, but so 0.5 sine of 1.27 degrees, which is 0.011 meters, which would be 1.1 centimeters, which is A. Moving on to problem number 7. So you have two boxes that are stacked side by side on top of a larger box as shown. All three boxes have mass m. The coefficient of static friction between the left box and the bottom box is mu s, and all other surfaces are frictionless. So we want to find the minimum value of mu s so that the upper boxes do not slide. Okay. So if we think about this problem here, so if the upper boxes don't slide, that means they're not going to move with respect to this. So this basically creates like a system. So it's like you're basically moving an equivalent mass of 3m at some acceleration a. And so the reason that if you have like a block on top of another block and you're pulling on this with force F, the reason this does not slide for like small values of F is that you have friction acting on it that basically allows it to accelerate with this block. So in this case, we have friction, but it's only acting between these two. So basically what's happening here is that for these two to not slide, friction has to um, accelerate both of these blocks. So we have a mass 2m at the same acceleration a. And so we want to find mu s. So we know that mu s in terms of fs is going to be, so fs equals mu s times n. And since it's only between these two, the normal force is going to be the weight force of mg. So fs equals mu s mg. So if we're solving for mu s in terms of f, what we can do is that we can divide these two equations to get rid of a. So we get 3 over 2, which means that fs is simply 2f over 3. And so mu s is 2f over 3 mg, which gives us d. Okay, next problem, problem number 8. If two stars, alpha and beta, with masses satisfying, so m of alpha over m of beta equals 10, and they're in circular orbits around each other. So in the rest of the system, find the ratio of the speeds v alpha and over v beta. Okay, so if you have like two massed objects, say this is m and this is m prime, and when you're given that they're moving in circular orbits around each other, it does not mean that both of them are moving in this path. It does not mean that, okay, m is moving like this and so is m prime. It means that they're both orbiting around their common center of mass. So if this is more massive than this, then center mass can be closer, and so it's gonna move or rotate. It's gonna orbit around its center of mass, and then so is this. This is gonna orbit around the center of mass in a circle, which means that this is only gonna be satisfied. So two massed objects are only gonna move in the same circular orbit around each other if they have the same mass, because their center of mass is gonna be halfway. So they're both gonna, orbit in the same circular orbit. But that's clearly not the case for this one, because we have that m alpha over m beta equals 10. So what we can do is that we can draw it out. So we have m alpha, m beta, and so we know that this one is more massive, so center of mass can be closer. And so what this means is that if this distance is like L, then the center of mass can be 10 times closer to m alpha because it has 10 times more mass. So it could be like 10L over 11, and then, sorry, it's 10 times closer. So L over 11 and 10L over 11. And we also know that both of them are exerting the same force on each other, which means that the centripetal force required for m alpha to move in a circular orbit around its center of mass is going to be equal to the centripetal force required for this one to rotate about 10L over 11. Okay, so if we equate the centripetal forces, so the centripetal force required for m alpha is going to be m alpha times v alpha squared over L over 11, so equal to m beta times v beta squared over 10L over 11, which basically means that m alpha v alpha squared times 10 equals m beta v beta squared. And since m alpha equals 10 m beta, I can replace that 10 m beta. Okay, and so we're asked to find v alpha over v beta. So we know that v alpha squared over v beta squared is m beta over 100 m beta. So v alpha over v beta is just 1 over 10, which gives us b. Okay, next problem number 9. So we have a helium balloon that's released from the floor in a room at rest, and it slowly rises and comes to rest, touching the ceiling. So the gravitational potential energy of the balloon has increased during this process. So since energy is conserved, the energy of something else must have decreased. So which of the following is the main contribution to this decrease? So, okay, let's try to look at each choice and see which one seems the most reasonable. So A is definitely incorrect, because it starts at rest and then comes to rest touching the ceiling, which means that kinetic energy is unchanged, so it's not A. The B is the elastic potential energy of the balloon has decreased, which is actually definitely possible. So this could be one of them. C, the thermal energy of the air in the balloon decreased, which has little relevance. So I think thermal energy, so C and D are both wrong. And E is the gravitational potential energy of the air in the room decreased, which is probably the correct answer. Because if you have the helium balloon, and this is the ground, this is the ceiling, and it moves up, what's happening is that the space that it occupies, so it moves up here and goes up. The space that it occupies is gonna basically drive all the air that was initially here down, which is definitely gonna reduce its gravitational potential energy. So I guess this is the most like relevant to what we're talking about. So it should be E, because basically the air is displaced due to the direct motion of the balloon. So there's a direct correlation between those two energies. Okay, so for problem number 10, we have an archer takes aim at a target that is 100 meters away, assuming that she holds the bow at the same height as the center of the target and shoots an arrow with a velocity v equals 100 meters per second. At what angle should she aim the bow so that the arrow hits the center of the target? So for this problem, so basically launch an arrow to this target. So you launch it to this target, which is 100 meters away, at a velocity of 100 meters per second. And you want to find the angle. So what you can use for this problem is that it ends at the same height. So it starts and ends at the same height, which means that its horizontal range is 100 meters. So the range formula is v0 squared sine 2 theta over g equals 100 meters. So we're given v0, which is 100 squared. So it's just sine 2 theta over g equals 1 over 100. So sine 2 theta equals 1 over 10. So 2 theta equals arc sine of 1 over 10. which means that theta equals 1/2 arcsine of 1/10, which gives us d. Okay, problem number 11. A projectile that is thrown from a horizontal surface and reaches a maximum height h, and also lands a distance h from the launch point. Neglecting air resistance, what is the maximum height for a projectile thrown directly upward with the same initial speed? So there are two formulas we can use here. So one is, so maximum height formula is going to be v0y squared over 2g, where v0y is just the initial y velocity, and we're given that to be h, and we're also given the range to be h, which is v0 squared sine 2 theta over g. So if we equate these two quantities, so you know that if it's launched at an angle theta, then v0y squared becomes v0 squared sine squared theta over 2g equals v0 squared sine 2 theta over g. So these cancel out, these cancel out, these cancel out. So we're left with sine squared theta equals 2 sine of 2 theta. So if we expand this, the sine 2 theta is just 2 sine theta cosine theta. So we get rid of this. So that tan theta equals 4. So arctan of 4, if we use our calculators, we get that it's 76 degrees. And so we're asked for the maximum height if it was thrown directly upward with the same initial speed. So what we know is that v0 squared sine squared theta over 2g is h. And we want to know what v0 squared over 2g is. So what we can do is just divide this by sine squared theta, and we get 17h over 16, which is a. So moving on to problem number 12. So you have a block of mass m that's initially held in place by two massless strings as shown. So the tension in the diagonal string is T1, so this string, and next the horizontal string, which is this one, is cut. And immediately afterward, the tension in the diagonal string is T2. Okay, so basically what you want to do is you want to find a relationship between T1 and T2. So have this configuration. Mass m. Okay, so you know initially there's no there's no vertical acceleration. So weight force, and then you have T1, and so this is theta, and you know that T1 sine theta equals mg. So this is the initial configuration, and then you know that later on when you cut the horizontal string, what you can realize is that so you have like a pendulum, and the ball is initially at rest. You know that since centripetal acceleration equals v squared over r, there can be no centripetal acceleration when it's at rest, because v is 0. So similarly, in this case, when the horizontal string is cut, it has no speed, which means that along the direction of this string, there can be no force. So what we can do is that you can notice that, okay, the tension is T2. There's gravity acting downward, and so the component of gravity in this direction must be equal to T2 for there to be no net force over here. So like we did here, we can say that, okay, this is theta, which would mean that this is 90 degrees. So this is 90 minus theta. And so this is theta. So mg sine theta equals T2. So T2 equals mg sine theta, which means T2 equals, sorry. So which means, if we compare it to T1, which is actually mg over sine theta. So we know that, therefore, T1 has to be greater than mg, and mg has to be greater than T2. So this is our answer, which would be B. So moving on to question number 13. So you have a uniform box with mass m that's at rest on a horizontal surface. Coefficient of static friction is mu s, and you're given that the force F is exerted at an angle of 85 degrees with the horizontal. So it'll eventually slide or lift off the ground. And so you want to know whether it will slide or lift off the ground and whether it's dependent on mu s or not. So what we can do first is that we can figure out what the conditions are. So to lift off, you know that, okay, the forces acting on the box are mg, gonna be your force F, and also normal force from the ground. When it lifts off, your normal force is 0, which means that F sine theta simply has to be equal to mg. So this is the condition to lift off. And then to slide, well, we know that, so F cosine theta must be equal to the friction force, Fs, which is mu s times n, mu s n, where n is going to be mg minus F sine theta, because as you increase F, you're increasing the vertical force on the block, which is going to reduce the normal force. So if we solve for F, we get that it should be mu s mg over cosine theta, plus mu s sine theta. Okay. So what we can do now is how we can plug in like various values of mu s, and see how this, so the sliding cutoff varies with the liftoff cutoff. So if we plug this in, so it should be mg over sine of 85 degrees. We get 1.0038 mg. So let's see how this compares to that for various values of mu s. So if mu s equals 1, it's going to be mg over cosine 85 plus sine 85, which is 0.92 mg. And then if we look at the answer choices, it says that for a certain value of mu s, so tan 85, it's going to produce different results. So why don't we plug in mu s equals tan 85 and see what happens. So tan 85 is 11.43. So plug in 11.43 mg over cosine 85 degrees plus sine 85 degrees times 11.43. We get so 11.43 divided by cosine of 85 plus 11.43 times sine of 85, which is 0.996. So as we can see, it doesn't matter what you use from US. I mean, it's always going to be less than 1.0038. And if we plug in like 100 just to confirm, so 85 degrees plus 100 sine 85 cosine of 85, 100 sine 85. So you get 1.0029. So it's never going to exceed this value, which means that it's always going to be easier to make it slide. So for any value of mu s, the box will slide first. So D is our answer. Okay, moving on to problem number 14. So we have an object, and so we want to find the fraction of its weight that rests on the left leg. So for problems like these, where it's asking for like the fraction of weight that's resting on something, what we can notice is that if there's like a weight force, say W, acting here, that's going to be equal to the normal force exerted by the table. So we can use that fact. So say this is N1, this is N2. So other forces are mg on this one, mg on this one, mg on this one, since they're all identical. And so since we want to find N1, what we can do is we can balance torques about this because it's in a static equilibrium. So if we balance torques about this point, since we don't know N2, so we only have one unknown. So N1 times, if we say that this distance is, 2L, so then that means this is L, which means this is L over 2. So it'd be equal to mg times 3L over 2 plus mgl, sorry, not mgl, mg times L over 2. So for this one, and then plus mg times L over 2 for this one as well. So we cancel out L. We get this, which gives us N1 equals 5 mg over 4. So since we want the fraction of the weight that rests on the left leg, so we want to find N1 over N1 plus N2. And so we know that N1 plus N2 is just like the total weight of the entire thing, which is 3 mg. So we just get 5 over 12, which is E. Okay, moving on to problem number 15. So we have a plot of the speed at which stars orbit a galaxy as a function of their distance r from the center. So assuming the galaxy has a spherically symmetric mass distribution, which plot best shows the mass of the galaxy m of r enclosed within radius r. So what we can do is we can try to relate the speed at which stars orbit the galaxy to the mass. So we know that the only force that's acting, so if we have like a star of mass m and like let's just say that distance r, which means so we're considering m of r, then g m of r times m over r squared, which is the force that this is experiencing, is equal to the centripetal force required to keep it in motion, which is mv squared over r. So if we try to solve for m of r, then we get m of r times g over r equals v of r whole squared. So m of r is equal to r times v of r whole squared over g. So we know that g is just a constant. And v of r, if we look at the graph, it's basically constant over time. So we can assume that both of these are constants. So it's just like equal to k, which is a constant of proportionality, times r. So since we're asked to find a plot of m of r with respect to r, it's basically linear, which best matches B. For problem number 16, we have a bead attached to a string of length L equals 10 meters. It's released from a very small angle theta 0 to the vertical, and a wall is placed in the path of the bead such that the bead collides elastically with the wall when the string is at an angle theta 0 over 2 to the vertical. What is the time interval between the bead's collisions with the wall? So the key realization here is that when the bead collides with the wall, it's basically gonna move as if it went all the way up and then came back down. So you're basically skipping this part of the oscillation. So our goal is to figure out like how much like time elapses in this part of the oscillation and then subtract it from the overall time of oscillation. So then we know that the overall time of oscillation can be found with t equals 2 pi root L over G. So L is given to be 10 meters, which means that our overall period of oscillation is 2 pi. And the time that the bead takes to go from here to here, so theta 0 over 2. So from here to here, well, we know that since it's an oscillation, we can approximate its path using the sine graph. So if this is like the angular displacement, and this is time, and we know that for a sine curve, what we want to figure out is how much time elapses between t equals 0 and the time that it reaches theta 0 over 2. So we basically want to figure out the angle for which sine of x is equal to 1/2, which is x equals pi over 6. So that means time is going to be pi over 6. And we know that the time to reach here, which is basically the time for the bead to move all the way up, is pi over 2. So what that means is that this time is pi over 6, and this time is pi over 2, which means that the the time interval that we're subtracting is 1/3 of this time. So basically what that means is that for our oscillations, we have this entire time interval, but we only have 1/3 of this time interval. Which means that of the entire oscillation, we're only going to have 2/3 of it, because the average of 1 and 1/3 is 2/3. So 2/3 times the total period of oscillation, which is 2 pi, gives us 4 pi over 3, which is C. Okay, moving on to problem number 17. So we have 3 physical pendulums, and we want to find the correct ranking of the moment of inertia of them about the points that they're pivoted about. So the first one is just like a string with a mass m connected to it. So a massless string. So the definition of moment of inertia is just the mass, so each mass, individual mass, times the distance from the pivot point squared. And so since there's only one mass, that's a distance L from the pivot point, its moment of inertia is ml squared. Uh, and then for the second one, it's a rod. So the formula, the moment of inertia of a rod about one of its ends is 1/3 ml squared. And then the third one is also a rod, but length 2L. So it's going to be 1/3 m 2L squared, which is 4 ml squared over 3, which means that I3 is going to be the greatest, which is greater than I1, which is greater than I2. So our answer is E, 312. Okay, next problem number 18. Alice, Bob, and Carol are each given identical airtight bags containing identical rocks and a large tub of water with a scale sitting on the bottom. So each of them measures the weight of their bag and rock by putting the bag on the scale using 3 different procedures. And we basically want to find the correct ranking of their measured weights. So Alice closes the bag so there's no air inside. So if we draw that out, basically look like this. We have a scale. Okay. So it's basically having a having a rock, right? Because you have a bag around it with no air. And then Bob's fills the rest of the bag with water before closing it. So you have the ball. We also have a bag around it with water inside. And then Carol closes the bag loosely so it has some air. So this is like water, but this is just air. So this is A, B, and C. Okay. So intuitively, A and B should be the same because both of them are essentially surrounded by water. So the weights should be equal. And then for C, it should be different because uh, basically the forces acting on the rock are mg, so you have the weight force, and a buoyant force, where the buoyant force is equal to rho vg. So it's dependent on the volume of water displaced. So if the weight of A equals weight of B, then how would the weight of C compare to both of these? Well, you have air around it, which means that it has greater volume. So it's going to have more buoyant force, which is going to mean that the scale is going to have to exert a smaller normal force in order for N plus buoyant force to equal mg, since this is also already much larger than A and B, which means that WC is going to be less than WA and WB. So our answer is E. So moving on to question number 19. So we have a student who sets up a simple pendulum with a length of 0.5 meters, a period of 1.4 seconds. And using this data, the student computes the acceleration due to gravity. And so you want to find the uncertainty of the measurement. So whenever you have uncertainty problems, we always want to solve for that variable and get an equation in terms of it. So in this case, we want g to equal some expression of t and L. So we can square both sides, and we get that this is G. So the uncertainty formula for division says that uncertainty over G equals this. And so now the issue is that although we have all these quantities, we don't know what the uncertainty of t squared is. So whenever we have like a equals b to the x, the uncertainty of a over a equals x times the uncertainty of b over b. So in this case, the uncertainty of t squared over t squared equals 2 times the uncertainty of t over t. So the uncertainty of t squared equals 2 times the uncertainty of t times t. So now we're solving for the uncertainty of g. It's going to be this. And so if we plug in all these quantities, so 10.1 for g, so on, we get a value of about 1.4 for the uncertainty, which gives us C. So for number 20, we have a mass oscillating like a pendulum, and we want to find a graph of the curve over complete oscillation. So what we can realize for this is that we can basically consider when, so it's horizontal and vertical velocities are 0. So obviously when it's at rest on either side, then Vx and Vy are both 0. And when it's in the middle, since it's moving completely horizontally, Vy is 0, but Vx is not equal to 0. So we can basically look for these points on the graph and see which one matches. So A and D are incorrect because they don't consider when both of them are 0, because they don't have a point at the origin. E is also incorrect because it doesn't have a point where Vy is 0 and Vx is not. And with similar logic, B is also wrong because it doesn't have a point where Vy is 0 and Vx is not, which leaves C. For 21, we have a smooth ring of radius r and mass m. And you have a point mass, which is also of mass m, that's given a speed v tangent to the surface of the ring. And you want to find the time it takes to return to its initial position. So the key word here is that's a smooth ring. So if you have a smooth ring, that means it's frictionless. So whenever you have like a block and it has a smooth surface, that means it can only exert forces that are perpendicular. It can only exert a normal force because there's no horizontal friction. So similarly for this smooth ring, we know that at all points, the force that it exerts on the ball is going to be perpendicular. And since the ball is moving tangent to the inner surface, the force that is going to be exerted on the ball is going to be perpendicular to the velocity. So it's going to do no work on the ball, which means that its velocity is going to stay constant throughout. So the time is just going to be the circumference over the constant velocity. So it's going to be 2 pi r over v, which gives us C. Okay, for problem number 22, so we have two springs, you can say K1 and K2, that are connected in 3 different configurations. And we want to figure out the relationship between Ka, Kb, and Kc. So Ka and Kc are actually pretty common. So we can start with those. So Ka is Ka, so K1 and K2. So whenever you're finding the effective spring constant, you can always consider stretching it by a small distance x and seeing what happens. So in this case, if we say that it has an effective spring constant of K effective, then K effective times delta x, which is the overall force generated by the springs, is going to be equal to K1x plus K2x, because both of them are stretched by x. So K effective equals K1 plus K2. So Ka is just K1 plus K2. So if we look at Kc, um, they're in series. So if we stretch it a distance x, it's going to be K effective times x. So now this is going to be different because we're given that the springs are massless. And so whenever you have a massless string and you pull on it with tension T, then there's always a constant tension throughout. So we can use the same logic in this case. So now we're pulling on it, which means that K1, say it's stretch a distance x1, this is stretched x2. Well, first of all, x1 plus x2 equals delta x. And also the tensions must be equal. So K1 x1 equals K2 x2. And so the spring force exerted by the two is going to be equal to K1 x1 plus K2 x2. And since they're equal, we can just say it's 2K1 x1. Now we want something like the expression we got here. We want it in terms of K1 and K2. So what we can do is we can try to eliminate delta x and then try to eliminate x1. So first of all, delta x is just x1 plus x2. And we know that x2, if we want to write it in terms of x1, so we can cancel x1 out, it's just k1 over k2 times x1. So now we can cancel out x1 and get that k effective is 2k1 over 1 plus k1 over k2, which is 2 k1 k2 over k1 plus k2. Kc is 2k1 k2 over k1 plus k2. Did something wrong here. What the hell did I do wrong? Oh, okay, got it. Okay, got it. So now for Kc, which is basically we have two springs that are in series. So again, we can consider stretching it by delta x. So we know that the springs are massless. So whenever we have like a massless string and we pull on it with tension T, then there's constant tension throughout because it's massless. So similarly in this case, um, if we just say that since we stretch the whole thing by delta x, this one stretches by x1, this one stretches by x2, then x1 plus x2 equals delta x, and the tensions are the same. So we can write either one of these as the resultant spring force. So now we want to get something in terms of just K1 and K2, like we did for Ka. So we can first replace delta x. And then we know that x2 is just going to be, so we have k1 x1 equals k2 x2. So it's just k1 x1 over k2. Then we can cancel out x1 and get that k effective equals k1 k2 over k1 plus k2. And lastly, for kb, which is a tricky one, so we notice that it looks very similar to ka, except there's a pulley. So how do we deal with this pulley? Well, we know that since this pulley is massless, then the net force on it must be 0. So if we consider stretching it delta x once again, then we know that if this one is stretched by x1 and this one is stretched by x2, then delta x is going to be x1 plus x2 over 2. And k effective times delta x is going to be the spring force that they both exert, which is going to be k1 x1 plus k2 x2. And since k1 x1 is equal to k2 x2, we can simply write this as 2k1 x1. So just like we did for for kc, we can write this 2k1 x1. So k effective times x1 plus x2 equals 4k1 x1. Now if we look back at the previous one, we got a very similar looking expression. So the only difference between this and this is that now we have 4k1 x1, which means that our answer will just be 4 times what we got for kb. So kb is just going to be 4 k1 k2 over k1 plus k2. Now if we compare these, so we have that ka equals k1 plus k2, kb is 4k1 k2. So we can just choose arbitrary quantities for k1 and k2. The only thing that we're given is that they have different spring constants. So we can say that k1 is 1 and k2 is 2. So that would be 3. This would be 8 over 3. And this would be 2 over 3. which means that KA is greater than KB, which is greater than KC. So it's A. Okay, problem number 23. Have an astronomer on Earth observes a star in galaxy, and the angular distance appears to vary with the minimum in January and a maximum in July. Uh, and so you want to find the ratio between the distance from the star, the distance to the star, and the distance to the sun. Okay, so what we can do is that we can basically draw out how this would look. So if this is the sun and this is the earth, now it's going to have an elliptical orbit around the sun. And if this is the earth in January, then this is the earth in July. And so we know that just because of this shift, there's a change in the apparent distance between the star and the galaxy of 0.5 arc seconds, which means that if this is a star, then this distance must be, so theta must be 0.5 arc seconds. So now what we want to do is we want to find the ratio between, so LS over this. So we know that this angle is going to be theta over 2. And so tan of theta over 2, which is 0.25 arc seconds, equals this, which is 1 over what we want to find. So our answer is 1 over tangent of 0.25 arc seconds, which gives us about 8 times 10 to the 5th, which is D. For problem number 24, so we have a very heavy plate that continuously moves up and down with a small speed v, and switches directions after each time t. And at a random time, a ball is dropped from rest above the plate and then bounces elastically off of it. You want to figure out how the ball's speed changes during this collision. This is actually a very interesting problem because, I mean, what you'd probably think is that, okay, since if the heavy plate is moving down and if the ball is also moving down, then the ball's going to slow down. But if the heavy plate is moving up, the ball's moving down, it's going to speed up. So it should be equally likely. But there's one small edge case, which is that if we consider let's say the zone in which the block moves. So this is going to be a distance v times delta t. Then what we can consider is that if the ball is dropped and let's just say it's at like the top of this zone, then when the ball is at the top of the zone, the block is equally likely to be moving either up or down, right? It can either be moving up or it's moving down. So it's like 50-50 probability. But even if the block is initially moving down when the ball is here, so let's just say it's moving down here, then for the amount of time that the ball takes to move all the way down here, the block would have already switched direction and is now going to start moving up. And so that's just one small edge case. That means that, so let's just say, right, it's like a 50-50 probability of the block moving up, so up or down. Now, just maybe like 1% of this 50, it's initially moving down and then it's going to start moving up. So just because of that one small case, it's going to be more likely to speed up, which means that the answer is D. And if you're wondering, this doesn't happen if the block is moving up, because like let's just say the block is here and it's moving up, and it's immediately going to collide with the ball. It doesn't have the time to like change direction and start moving down. So for problem number 25, we have a skier who slides from rest along a frictionless slope with an incline of 30 degrees for 150 meters. And then they transition to this jumping ramp here. And you want to know how far they'll travel horizontally before landing. So if we draw it out, so we know that it basically goes from here to here. And since this is 150 meters and you have that theta is 30 degrees, then the distance h it travels, so mgh is going to be equal to 1 half mv squared, where v is the velocity at this point. So h is just going to be 150 over 2, since this is 30 degrees. So it's just 75, which equals v squared. So v is just square root of about 1500. So this is our x velocity at this point. And we want to figure out what the horizontal distance is between here and the time it hits the plane. So if we consider the distance, the vertical distance it travels between here and here, and the horizontal distance, which we're looking for, we know that y, so delta y minus this distance, which is hr, so 5, equals delta x times tan 30 degrees. Because if we consider this, so this is basically y minus 5, and this is delta x. We know that since this is theta, this is also theta. So that means x times tan 30 degrees has to be y minus 5. So now we know that we can basically make this a quadratic equation in terms of time. So y is just 1 half gt squared. So we get 1 half gt squared minus 5 equals, so it's going to be our horizontal velocity times time, since the velocity is constant throughout, times tan 30 degrees. And then 1 half gt squared. So 1 half g is just like 5. So 5t squared minus root 1500 times root 1 over root 3. So root 3 over 3 times t minus 5 equals 0. So if we use the quadratic formula, we'll get that t equals root 6 minus root 5. Root 5 minus root 6, and root 5 plus root 6. So we want a positive solution for time. So it's root 5 plus root 6. And so our answer is just going to be root 1500, which is our initial x velocity, times time, which is root 5 plus root 6. And we get about 180 meters, which is C.